Continuing our discussion about capital budgeting, we talked about the 4 steps for the investment decisions. We're looking at the center pivot irrigation. We needed to collect the relevant information and lay out the cash flows. And then today we're continuing the steps to the 4th step, which is the analysis. And we're going to today look at the profitability. We'll also look at the sensitivity of this investment. The reading assignment, we're still in Chapter 10, but when we come back with new material, we'll be in Chapter 11, where we're going to be covering inflation, risk, and financial planning. The first step in the analysis is we're going to try to determine whether this center pivot irrigation system is profitable or not. And to start that process, we're going to calculate the net present value. But as part of the information that we need to collect, if we're going to calculate a net present value, in addition to all the cash flows, we also have to choose a discount rate. Because we've included taxes now in our cash flows, we also need to use a after-tax discount rate. Now, if we let the rate, this R superscript BT, represent the required rate of return to capital before tax, then we can calculate this after-tax discount rate by taking the before-tax rate and multiplying it by 1 minus the marginal tax rate. Now, in the problem, this farmer said that requires a 12.5% return to capital pre-tax, as other investments that will return 12.5%. Also, if you look at the fine print, it says that this farmer expects his marginal tax rate over the next 6 years to be 20%. So we take the 12.5% and we multiply it by 1 minus the marginal tax rate, or 80%, which is 10%. That means basically for every dollar invested, if that farmer receives 12.5% return and has to pay 20% of that to the bank, then that particular investor only gets to keep 10%. So that's the relevant rate, what that business gets to retain. Not what they overall make, but what they retain in the business after taxes. Now, if we put this into our chart, now, to calculate the net present value, we are going to find the present value of each of the components. We have cost, we have the after-tax net returns, we have the tax savings from depreciation, and we have the after-tax terminal value. First, the present value of cost. The first component, we can see that it is the $80,000 at time 0. Since it's already at time 0, there's no discounting that needs to take place. So we see that the present value of cost is the $80,000. The next component, which I've highlighted in blue, we're looking at the present value of the after-tax net returns. The nice thing is, notice that these after-tax net returns are uniform, and there are 3 payments. So we can take the $12,800, recognizing that they're uniform, we can use the uniform series present value factor. We had concluded earlier that the after-tax discount rate was 10%, and because there's 3 periods, we can plug that into our calculators as 3N, 10% I. The $12,800 is our payment. Zero out the future value, compute the present value, and it is $31,831. And we put it over here to the right to provide the present value of the after-tax net returns. The third component is the tax savings from depreciation. Again, I've highlighted it on the screen in blue. Notice, because we're using straight line depreciation, that it's a uniform tax savings for each of the 3 years. So again, we can use the uniform series present value factor at 10% for 3 years, multiply the factor by the 1,067. Now, if you're using your calculators to do this, okay, you only have to change one number. Just put 1,067 in your payment. You already have the N and the I in your calculator, so you just have to compute the present value. it comes out to be this 2652, and so we put it in our chart as 26. In this case, we rounded it off to 2653. Now we're looking at the fourth and last component, which is the after-tax terminal value, and we calculated that to be $60,800. And since that's a single sum amount at time 3, notice that we multiply the $60,800 by this single sum factor, discounting that single sum amount at 10% for 3 years. And your calculators, again, that's very easy to do because you put 3 in, 10% I, don't even have, those are already in fact in your calculator. You zero out the payment and you put $60,800 into your future value key, compute the value, and it comes out to be $4,680. Now that we have the present value of each of the 4 components, we sum them up to get the net present value. Now, what I've done in this equation at the bottom of this screen, if you look at it, this is just a summary of what we have done in the last 4 slides. We have the present value of the cost. We have the present value of the after-tax net returns. We have the present value of the tax savings from depreciation. And we have the present value of the after-tax terminal value. We can add the present value, and you'll see that that matches up to what we did before. Sum them up. So we're summing up each of these components, and you see that it comes out to be $165. You also see what I mean now by sequential. We have to solve piece by piece by piece by piece, and then we put it all together. But then what's our net result? We show that we have a net present value of 165. What is our initial conclusion based on the net present value? So you would say it's profitable. So this farmer demanded a 10% after-tax rate of return. Is the yield on this investment, based on the assumptions we made, at least 10%? Given that the net present value is positive, the answer is yes, so we can accept it. We don't know what its yield is yet. We're going to figure that out. Right now, all we can say is based on the net present value, it returns something greater than our required after-tax rate of return of 10%. So it is, from a profitability standpoint, acceptable. But we also have to ask the question, what is the yield? What is the true rate of return of this investment if the net present value is greater than 0? Let's put in showing how to solve the internal rate of return. Okay, I've repeated the previous slide where you can see the net present value calculated in all its glory. All the arithmetic is laid out. This is the equation for the net present value. How do we change and alter that equation so that we can calculate the yield? By definition, what do we do here? Okay, you set net present value equal to 0 by definition, right? Then you solve for the rate. You know, in terms of changing the equation, if you lay out the net present value, which at this point should be fairly obvious, to solve for the yield, set the net present value equal to 0 and solve for the R. And sure enough, that's what we do. The second equation now becomes the equation for solving for the rate. Now look at this equation and see how it shows up on this equation. I've just taken that bottom equation and transposed it onto this slide. I've basically broken it by each component, and this shouldn't surprise you. If we look at this equation, this first component is the cost. Second component is the present value of the after-tax net returns. The third component is the present value of the tax savings from depreciation. And the last component is the present value of the after-tax terminal value. Hopefully you're seeing that this isn't mystery, it's not even hard. If you look at each of the components that we go through, this equation, if you just looked at it, you might say, well, where's that coming from? Well, you can see. What did I say about the internal rate of return? There's not always a solution. There can be multiple solutions depending on the problem. So instead of just solving for it in your calculator, what are we going to do? We're going to search for it. And in fact, even if your calculator solves for it, it's going to do the same thing. Just got to go through a search procedure, and that's exactly what we're going to do now. So, to search for it, let's set up this simple chart that shows, okay, the rate as a function of the net present value. Now, every one of you can plug in a rate, so let's choose a rate. Doesn't make any difference, just grab a rate. We'll choose 9.5%, and we're going to plug that 9.5% into those three spots in your equation, and you're going to solve for the net present value. And if you do so, and you can feel free to do so and check my work, but I come up with $1,000. Now, we are trying to find the rate that makes the net present value equal to 0. So in this particular case, the rate is too low. We have to increase the rate. How much? Grab one and see. Let's try 10.5%. So we take this 10.5%, we plug it into this equation, and when we do it and we do the arithmetic, it comes out to a negative. So we see that the rate is somewhere between 9.5 and 10.5%. So we know it's lower than 10.5 but greater than 9.5, so let's try 10%. And 10% is easy because we already did 10%, right? And we remember that it came out to 165. So we now know that it's somewhere between 10% and 10.5%, and because the 10% is closer to 0, we know it's somewhere close to 10%. We could continue to do that as long as we wanted, continually narrowing that bound until we would find and discover that at 10.09%, the net present value is equal to 0. So what is then the yield on this investment? 10.09%. Just barely above what was required. Why were we trying to get that net present value to 0? Because by definition, yield or rate of return, or the internal rate of return, by definition is the rate that makes the present value of cash inflows equal to the present value of cash outflows. And by definition of net present value, which is the difference, if those are equal, then it's 0. This is the way on a multi-period problem that you can calculate that rate. Now, if you look now at these points, actually all these points, on a two-dimensional graph, where these points are the net present value and these points are the R, which I've done that for you. Taken these points, and we've graphed out the relationship between the net present value and the discount rate. As the discount rate goes up, the net present value goes down. In other words, if you have an investment with a fixed income stream, the more you require of a rate of return, the less value that investment is, because your income is fixed. Also notice that where this net present value crosses the y-axis, that is the yield or the internal rate of return. So you can visually see what's going on between the net present value and the discount rate. I want to show you that this last line is what we refer to as the net cash flow. And we're going to use that more in depth when we get into the financial feasibility or the liquidity of the investments as part of the analysis. For now, I'm going to show you also that if we sum up each of these columns, in time 0 we have an $80,000 cash outflow. In the second time period, we have a after-tax net return of $12,800, but we also have a tax savings because of depreciation of $1,067. So if we look at it then, and our cash revenues from this irrigation system, end of the first year is $13,867, and it's the same in the end of the second period. At the end of the third period, when we've decided to sell it, then we still have the net returns, the tax savings from depreciation, but we also have the after-tax terminal value, so we have a cash flow of $74,667. Now, if we want to calculate the net present value using these net cash flows, notice that this first $80,000 is at time 0, no discounting. And the second period is this 13,867, but notice that we only bring it back one period. Then in the second period, we bring it back 2 periods. And then this 74,667, we're bringing it back as a single sum amount for 3 periods. And if we do that, no surprise, the net present value comes out the same.